Okay.
Great. Okay. I love it when I get cut off in the middle. So, okay. So we're back here. So we're trying to do our best job of estimating which symbol was really sent, right? And so it's unlikely that we're going to guess this symbol if this one is sent. I mean, if it's really bad, who knows, right? But the likeliest mistake we're going to make is that adjacent symbol, the next nearest neighbor, basically. So what we'd like in case, if we're going to make an error, we'd like to make the smallest error possible, right? So that's why we use a gray code. If we pick accidentally or mistakenly pick the nearest neighbor, then we know that we're only one bit off rather than being more than that. Okay. So gray code from one perspective is just a rule, right? That as you move from one to the nearest neighbor, whichever direction you go, you should only change one bit. And that's a rule. But I want you to also understand why we have that rule. Why do we use a gray code? So make sure, I know sometimes you're under a little stress when you take a test, but make sure you satisfy everything that I asked for, right? So I don't know, some people did one and not the other, but maybe you're just stressed and trying to get through the test fast, or maybe you didn't know how to do it. But yeah, make sure you answer the whole question, right? So all right, 13. So this one was actually complex, but I basically we went over that in class as the exercise or the example that we derived for quadrature signaling, and basically told you to take note of that, right? So um, try to give you guys a good idea on what I think. I test you on things that I think are important. Doesn't mean that everything I say isn't important, but I know that there's a lot of material you cover in a bunch of lectures and stuff. So yeah, when I'm trying to highlight something and say you might want to study that for the test, then please take note of that and be prepared. So this is pretty much straight out of that example. And here some of the key things are that well, they're equal probable, um, which gives us access in certain formulas that we can use, right? It's binary signaling. That means that there's only two symbols, right? We're signaling two um, two symbols. So some people drew out some constellations with many different constellation points. Some people, I think, maybe saw the word quadrature and said there must be four symbols there. I'm not sure. But really, the binary signaling is telling you that there's two symbols. The quadrature is reflecting to the relationship with each other, right? And so I go ahead and give you that information here and saying that symbol one, we have two symbols, symbol one and symbol two. And that one is going to be at coordinate, the root of the energy per bit, comma 0, right? So it's on the real axis. And S2 is on the imaginary axis, so it's in quadrature with the other one. So not sure if you use that term. I would think that you've dealt with complex math enough that that would be familiar to you. If not, yeah, that's what we mean. Regardless, that was laid out in the example we covered. So here I gave you a signal noise ratio or the bit energy to the noise energy. You can, I use both energy and power, and we know that they're related. Power is energy in a particular time, whereas energy is overall time, right? So but as long as you're in a ratio, you really don't care, right? So that time will cancel out. So we often, even though we have energy up here as this E script E, just conventionally you're often working with powers because our signals tend to go on kind of quote unquote forever. Nothing is forever, but our radio signal is out there signaling. Right. So all right. So I try to make it easy here. 16 is the ratio, and I also provided the information in logarithmic form and the decibels. That was really to make sure that you didn't confuse 16 as being in decibels. That's the linear version of it. All right, so now let's sketch a constellation and show the decision boundaries. So I give you the coordinates there of these things. So that's what I kind of expected you to do, is locate these. Perhaps on my solution, I should have some subscripts on these. So this would be S1, and that would be S2 up here, right? So I think I cut and paste this from the PowerPoint, so I can't edit it right here. So this becomes one decision area, this becomes the other decision area. And so I guess it depends on, I think I made this mistake in the PowerPoint, but I thought I corrected it. And so if this is S2, this is a decision area for S2. And if this is S1 down here, then this should be the decision area for S1, right? So we can do kind of our rules. So what do I say? I say sketch constellation. So that's locating these points on the axes, and show the decision area boundaries and areas, right? So you have two symbols, so you'll have one decision boundary, and that would be a line that, again, we can apply our rule, connect these 2 points with a line, bisect it perpendicularly with your decision boundary, right? I think you can look at this if you really understand the concepts that we're trying to learn here. I think this could be done by inspection, right? So what you're trying to do is delineate these decision areas so that, if a point falls somewhere, how do you choose which symbol to apply that to, right? So if things are equal probable, then we can do this approach. We don't have to weight it one way or another. If something's falling in this region, it should be mapped to that symbol. If something's falling in this region, it should be mapped to that symbol. So so you should end up with a drawing that looks something like this, maybe labeled a little bit better, but just get there. So now B is a little bit more involved, but really it's not that scary if you've looked at this and understand the concepts. during the lecture, I made a point about with this, you need to figure out what rho is. What is that correlation coefficient, or um, how do these two symbols correlate with respect to each other? Well, we said they're in quadrature, and that means that rho is going to be 0, right? In the PowerPoint presentation, let's see. Oh, that's today's. Anyway, I kind of asked on what slide what rho is, and then on the next slide I showed the curves, plotted curves from the book, and it says rho is equal to 0 right there, which I pointed out. So that is the insight that you want to make, is that rho is equal to 0. So then you're going to look at these equations here, and you're going to say, okay, well, it's equal probable, so I can use this equation, but what is this D12? Well, you could use your geometry, Pythagorean's theorem, and figure that out. Or you can use this relationship right here. And so I put this in here, but really you're writing, I gave it to you in vector form, so you don't really know these t's and y's of t, but the insight is that they're in quadrature, and so their correlation is 0. So you plug in 0 here, and you end up with 2 times e. So that's d sub 1 2 squared, and you can put that up there. And I've given you this signal noise ratio, so you can put the energy in terms of the noise, or the noise in terms of the energy. You should have enough information there. So basically you're going to end up with 2 times the energy here. That just becomes 1. And substitute in what do we know about the energy? Well, it's 16 times n and naught, right? So our just this equation there, just say solve for EB, that's 16 and naught. So multiply that by 2, that's 32 and naught. You got 2 and naught. The noise terms cancel out. You're left with square root of 16, which is 4. Go and look up Q is equal to 4 in the table, and that's this this entry right here, 3.167 times 10 to the minus 5th. Apply a sanity check. Yeah, during lecture I mentioned that 10 to the minus 5th is often our kind of benchmark of where we're looking at errors and stuff. So it's not a ridiculous, I mean, it's a very small number, sure, but it's not a ridiculous number. Okay. All right, so that's the exam. If you have questions, I mean, I could entertain a question now, but feel free to join my office hours and we can go through your exam. And again, apologies. Normally I try to give you some feedback as I grade these things, but unfortunately I lost it all. All right. Let's look at then more of a lecture here. How much time do we have? Okay, that's reasonable. Whatever, away. All right, so all right, I guess you're seeing my outline preview.
Yep.
On here, but that doesn't matter. Yeah, so we've reviewed the test. Now midterms are unfortunately due on 3/9. It had been nice if I We could have squeezed in a test on 310. It would give us a little bit more time to learn some new material, and all. And then I could rush to grade them and get grades turned in. But unfortunately, the grades are due on Thursday, so that means our next test is Tuesday. That's not far off. So we have today's lecture and 2 more next week, and then a test again. So hopefully we'll include a little bit more information that I can test you on, but I think the midterm, you can expect us to go back and maybe cover some of the issues from this test, make it a cumulative exam, and maybe to go a little deeper. I will try to give you a test preview. I don't want to take up too much lecture time though, so we'll just provide that, and hopefully you guys understand how I test a little bit now. May or may not be similar to other professors you had, but we got that first one out of the way. So hopefully the second one, if you did great, hopefully you'll do great again. If you didn't do so great, hopefully you'll do great this time. So homework 2, yeah, because of this grading snafu with Adobe crashing on me yesterday, I didn't get a chance to select any homework assignments, but I'll try to do that and get that posted on Moodle soon. And so we'll have a chance to do some reinforcement learning, and then I'll be able to draw from the homework for the exam. So again, there's not too many surprises. So all right, now let's cover a little bit of new material, correlation receivers, and that. So all right, so yeah, same format, prior material, but maybe at a deeper level, and include some new material. All right, so on the correlation receiver, we've learned how to design our decision area boundaries to produce an optimal receiver, right? And we kind of have these rules that we can follow. We've got kind of a mathematical basis, and we've with formulas, and we've got some graphical tools that we find that are handy by drawing out these constellations to help us visualize what's going on. So it's not just math. Eventually, if you work with math enough, you kind of begin to see it intuitively, but these constellation diagrams are really there to help us, be able to visualize what's really going on, right? We've understood that if we can make some assumptions, like the symbols are going to be equal probable, then we can simplify things, and both our math and our decision areas are a little bit easier to deal with. But we've also learned that this maximal a posteriori probability receiver, it's a mouthful, is an optimal receiver, and it chooses the symbol that corresponds to the maximal a posteriori via probability via Bayes' theorem, right? So some of y'all recognize that on and made note of that on a test, even though I really wasn't yet. We didn't actually test on the map and stuff. So but yeah, that's it's the idea that at the receiver we're trying to look empirically, what we're making observations, and we're trying to infer what was actually sent, right? So the maximum likelihood receiver is simpler when we know that that the transmitted symbols are equal probable. So we know all that, right? So but that still may seem quite abstract, right? So now how do we actually get around to implementing this? So we'll go another little layer deeper. I mean, we're not going to write C code here or try to design any circuits yet or anything like that. But we're going to implement this in some blocks, let's say, right? So our map and ML receivers were derived using the vector form and constellation design. That's easy. We like working with vectors. You may not think so, but the alternative is worse. But yeah, we build up these tools, and we know how to work with vectors, and we know what they mean and that type of thing, right? So and then we can use them to visualize these things, and we're not having to draw these symbols over time or that type of thing. We can just identify it with a dot on a constellation, right? But the receiver is not seeing that. The receiver is seeing some voltage that varies over time, hopefully in a predictable and repeatable manner, but it's also corrupted by all sorts of noise, right? So we're not dealing with an instance in time. So we need to kind of be able to teach that receiver how to convert from those vectors back into or the functions over time, the symbols S of t, into the vectors, so that then we can apply all these rules that we just developed for the map and the ML receiver. Right. So we can return to the orthonormal basis function concept and convert the signals as a function of time to vectors as coefficients of these orthonormal basis functions. Now, we're not going to go into those formula today, but instead, I think we'll focus on the block diagrams, and then we'll try to fill in the blanks next week. So we have this signal coming in way over here on the left, R of t, right? And now we can split that R of t out into multiple parallel paths, and we can multiply it by one of n basis functions, right? So this is our conversion between the vector and analog or time signal representations of this received signal, right? So these are the basis functions. Think Fourier series expansion, for example, right? Fourier, a exponential or a cosine Fourier series expansion is one example of a set of basis functions, right? So this could be cosine omega t, this could be cosine 2 omega t, this could be cosine n omega t as a basis function, right? And so we're going to take this R t and we're going to multiply by those basis functions. We're going to integrate over that pulse period, right? And then that's going to give us these coefficients of the vector, right? So a vector, if you remember, okay, let's just look at a three-dimensional vector in Cartesian space, right? So you have the unit vectors, u sub x, u sub y, u sub z, and then you have coefficients times each of those, right? Maybe you label them a sub x, a sub y, a sub z, right? And that creates a vector in three-dimensional space, or simplified to 2 dimensions, just do x and y, right? When you write down that vector, you could write it out as a mathematical summation of a sub x times the u sub x unit vector, or plus a sub y times u sub y unit vector, plus a sub z times u sub z unit vector. Or sometimes we use like ijk or something like that when we're dealing with in the complex plane we'll do that sometimes. So the so that's that's a concept of a vector, and then we know that those unit vectors define an orthogonal coordinate space, right? Or to use our terms here, a basis set. So that ux represents the x-axis, but it's normalized to have a length of 1, right? And u sub y represents the y-axis, and we know that that is, in a Cartesian system, that vector is orthogonal or perpendicular to the x-axis, right? U sub z is represents the unit vector along the z-axis. It is also orthogonal. In fact, they're all mutually orthogonal, right? The uy is orthogonal to the uz, is orthogonal to the ux. So these are trying to help you relate this to something that you are familiar with, right? So when we deal with these vectors, we know we've adopted a particular coordinate system, right? So you're working in 3-dimension Cartesian coordinates, you know what your unit vectors are. So if you want to write down your vector in shorthand, you can just like do a parentheses and put ax comma ay comma az, and just write it in shorthand. That's what we're doing here, right? It's it may seem complex, but that's because ultimately we got to do all the math, but that's what we're doing here. So R1 is the coefficient of that first basis function. We'll call it a unit vector, but it's a basis function, right? So and it's just a little bit more complex because it has a dependency over time, right? But this phi1, phi2, phi n, they're all mutually orthogonal to each other, right? And then these r's are just our coefficients that describes that vector. We sum all those up, and r now is just that vector, just like we'd have ax plus ay plus az with the unit vectors on them, right? So r is just a vector. Now that we have the vector, we have the received signal in vector form. Now we can correlate it. So this is a correlation receiver, and we can correlate it with S1, S2. These are vector form of the symbols that are in our constellation set, right? And so now we do the we correlate that. We essentially do a dot product for all of these, and then we have this eta, right? So what is this eta? Well, that's that funky little thing we had in our map receiver that encompasses some of those bias terms, right? And the bias terms aren't that important, except when you don't have equal probable symbols to begin with, right? So if they are not equal probable, then we end up with these bias terms here, right? So that's what's happening here. Now, these dot products are essentially the projection of this vector r onto these different symbols. All right, so the dot product does this projection onto two vectors to each other. So it's kind of showing how similar are they, right? The more similar they are, then the larger this value is going to be, right? So now this output, a dot product of two vectors, is a scalar, right? if you remember from your math methods or whatever, you take that dot product and of two vectors, and the output is a scalar. So now we're just dealing with the voltage or an amplitude. So we go through this bias process here, and now in this block we just look at all m of these. Right, there's m different symbols, and we select the largest. And that's our best estimate. Okay, and we go with that, and we repeat that for every symbol that comes in. There's a process outside of this diagram that does all that timing, trying to figure out when does the symbol start and when does it end, and when does the next one start and when does it end. There is a process and a receiver that does that. We call that timing recovery. Given that, then we just kind of repeat this process over and over again for every symbol. Now, we can simplify this, and the book goes into this, and we'll go into this perhaps on Tuesday. I'm sorry, and but you can reorganize this stuff, taking advantage of some math and some optimization type stuff, and we can just directly multiply the incoming time signal with the symbols in the time domain, integrate them, go through the bias process, and then do the thresholding. Okay, so this multiplication and then this integration will provide a scalar value coming out for each of these lines, and we again tweak those according to that bias term and select largest. So this is potentially a simpler approach. It really depends on the size of M and the size of N here, right? So we have 1 to M here, we have 1 to N there. So one may or may not be larger. It depends on these basis functions, the set of basis functions required to accurately represent this signal in this time domain signal as a vector, and versus your constellation size. So this is potentially simpler, not necessarily simpler. Now, these are both optimum, right? Because we're implementing that map receiver here. So this is an implementation of an optimal receiver. So as long as we don't make any compromises along the way, then this is an optimal implementation of an optimal receiver algorithm. Okay? Another approach that is likewise optimum is a matched filter receiver. And so here what we're doing is we run this through, and this is a little bit simple, but we create a filter that has the same spectrum as your symbols coming in, right? And then that filter shape matches the spectrum of the symbols S of t. If it's complex, we need to do conjugate, but in the for real signals, we don't have to worry about that. So and then we sample it, and then we go through a threshold again. Now, what this probably needs more explanation that we'll again do on Tuesday, but I wanted to introduce kind of the big picture concepts here. This is interesting here because kind of in a hand wavy kind of way, what we're trying to do here is we're trying to filter out the noise in such a way that we do the best job of filtering, getting rid of noise without getting rid of signal, right? Because at the end of the day, what matters is signal to noise ratio. If we have stronger signal, our job's easier. If we have smaller noise, our job's easier, right? To try to estimate what the right symbol was that was sent, right? So we're trying to maximize the signal, minimize the noise. That's essentially maximizing that signal to noise ratio. If we do that, we can do that by shaping this filter so that it matches the spectrum of the signal, because we don't want to kill any of it. But everywhere else, it gets rid of noise energy. So that's kind of a very hand-wavy way of looking at a match filter receiver. All right, I think that's it. So yeah, we're over time. So have a great weekend, and we'll see you next week.
Bye-bye.